Math and Beats. This video, we are going to look at an alternative notation for describing derivatives, and this notation is referred to as Leibniz notation after the mathematician Leibniz. So let's take a look here. All right, thus far we have determined that the derivative function right here, so far we've been calling it f prime of x, is determined by this limit as h goes to 0 of f of x plus h minus f of x over h. So we've talked about all that and what that means. And of course, that is going to be the derivative function provided the limit exists. And remember that this value of h in the denominator represents the horizontal distance between the two x locations, x and x plus h. It's just that horizontal distance between the two. And just as a reminder, as a picture, this is kind of the thing we should be seeing in the back of our head. You see the red line, the secant line connecting the locations of x comma f of x and x plus h comma f of x plus h. And of course, this distance between the two x locations, that's our h, right? The horizontal distance, and as we let h go to 0, then the slope of our secant line approaches the slope of our tangent line. So that's all stuff we've determined already, but in particular, this horizontal distance h is really where this new notation is going to play a role. So that's why I wanted to mention it here first. So, just keeping the picture above in mind, we could call that horizontal distance h really whatever we want, right? We just happen to call it h. So rather than calling it h, how about instead down here at the bottom, let's just call it delta x. So it's just like some change in the x direction, really. So I'm just calling it delta x rather than h now. Means exactly the same thing. So if I take my limit definition of the derivative function and replacing the h's with delta x's, we could rewrite the derivative function f prime of x as follows right here. So right here, this is what we already have, right? And then notice I'm just replacing the h's with delta x's, as we can see in this line right there. Okay, so there's what used to be h, there's what used to be h. I'm just calling it delta x. And of course, if we were letting h go to 0 before, then now we're also going to let delta x go to 0. So it means exactly the same thing. I'm just replacing the h notation with delta x because there's some change in the x direction. And then, of course, the numerator there represents the change in the output direction between the two x locations. So we could refer to that as some change in the y direction there. And so I could rewrite the limit right here as the limit is delta x goes to 0 of delta y over delta x. And then if we just write that limit like so, dy over dx, that notation right there, the dy over dx, is our Leibniz notation for derivative functions. So you may be wondering why we would introduce this notation or what is its use. And we will see in further videos that we can take higher order derivatives and it becomes a much more useful way of describing them. And moreover, there's some other things in this notation I want to talk about right now that is also of use. So when we write the dy dx described by the limit as delta x goes to 0 of delta y over delta x, we can be thinking of those two quantities dy dx as these limits that we see down below. Now, later in the discussion of calculus, we'll talk about a topic which is called the differential, and we'll get more into depth about this at that time. But for now, you think of the dx is like our limit as delta x goes to 0 of delta x. Now you might say, well, isn't that just 0? Well, think of it as an infinitesimally small, tiniest, arbitrarily tiny change in the x direction, right? And so that is what we mean by dx. And moreover, limit as delta x goes to 0 of delta y, that's what we're calling our dy, if you will. So that's the infinitesimally small change in the output or y direction as the input direction becomes arbitrarily tiny. And that ratio gives us the slope of the tangent line at x. And like I've already said, dy dx is our Leibniz notation for f prime of x. So really, if y is equal to f of x, then f prime of x here is the same exact thing as writing dy dx. Okay, they mean the same thing, different ways of describing the notation. Now, what does the notation tell us? Okay, so a couple things here. So keeping in mind again, dy dx for the function y is equal to f of x is our derivative function f prime of x. So when we write that notation, because the numerator involves change in the output direction, or y in this case, then when we write dy dx, it tells us that y is what we are considering to be the dependent variable. So that's always occurring in the numerator of that notation. And that's the variable for which we are differentiating, right? So to take a derivative of a function is to differentiate that function, but then with what variable are we differentiating with respect to? Well, that's that variable in the denominator we see there, the x. So it also tells us that the x is the independent variable. So that information is embedded into that notation there. Moreover, there's this operator sitting around. When you need to take a derivative, call the operator. The d dx by itself, we can kind of think of that as an action, a verb. D dx by itself is meaningless. It literally means take a derivative with respect to x, or differentiate with respect to x. But without some other variable that we're differentiating, that is just meaningless to write, other than just saying, well, that notation means differentiate something with respect to x. So once we go ahead and say, oh, I'm going to differentiate y with respect to x now, it then tells us, we're going to differentiate that output variable y, which is a function of x, with respect to x. So you can also imagine writing this as take the derivative with respect to x of some function f of x. So it kind of like apply the operation of differentiation to something, in this case a function f of x, or call it y if you want. And then what variable do we treat as the input variable? Well, that's that variable we see in the denominator there, that x, right? So we differentiate a function, f of x, with respect to x. And the d dx is that action, that verb to differentiate. Right, or take the derivative of, right? So you can use those two words simultaneously. And like I already wrote above, these are our various ways of writing single variable function derivatives at this point in time. The derivative function f prime of x is the same as differentiating the function f of x with respect to x, which is the same thing as dy dx, assuming y is f of x here. So we'll use those throughout the remainder of the Calculus 1 discussion, and we should be able to identify those things as we move along. Now, we can also use this notation for finding derivative values, right? So remember, f prime of x is the derivative function, right? It's the function that gives us the slope of f at all values of x for which it is defined. And remember, f prime of a is the derivative of the function f at a specific location a. Maybe a is 1, 2, pi, whatever, right? So it's different notation using the Leibniz notation compared to the derivative function, because now we are calculating a derivative at a particular location. So in order to use the notation for this, what we do is we introduce this like bar looking symbol down here that we see. And that whenever we write some expression, okay, so like you have some expression like so, whatever it might be involving, say, a variable x or whatever variable, if we write a little bar next to it, and then we say x is equal to some number a, what that literally means is this whole thing here. It means to evaluate the expression at x is equal to a. Okay, that's what that bar is telling us. Evaluate that expression where we have at the location x is equal to the number a. So you see down here, f prime of a, another way to write this is, well, just this piece right there, well, that's our derivative function, right? Differentiate f of x with respect to x. That's going to give us our derivative function. And once we obtain our derivative function, we can then replace the variable, the input variable x, with the particular number a. And so really what that's saying is evaluate the derivative function at x is equal to a, which is the same thing as just writing f prime of a. Or if you prefer, dy dx evaluated at x is a. They mean the same exact thing. So for values of derivatives, we've got to write that little bar, and then at the bottom of the bar there, we write x is equal to the location where we're evaluating the derivative at. So that's what all that says right here. I wrote it above, right? This all means this right up here. Writing that bar next to an expression means to evaluate the expression at the location of interest. X is equal to a in this particular situation. So now that we've kind of said all that, we're going to do a couple of examples here in which we just find some more derivatives using the limit definition. So we want to use the limit definition of the derivative to find each of the following. And so in part A, we have a function here. Think of this function, the square root of 3w plus 1. Think of that as a function of w, right? And so here what we're saying is differentiate that function of w with respect to w. Find that derivative function, right? This is going to be the result, which is equivalent to f prime of w after we find it. So let's find it using the limit definition. So this is the same as saying the limit as h goes to 0 of f of w plus h minus f of w over h. Now, like we've done in a previous video, let's go ahead and find f of w plus h so we can replace it in our formula. So up here at the top, f of w plus h is the same as the square root of 3, replace w with w plus h, so 3 times w plus h, plus a 1. And then if we just distribute the 3, we get square root 3w plus 3h plus a 1. So there's my f of w plus h, if you will, calling f of w here square root of 3w plus 1. So then let's rewrite this. This is the same as the limit as h goes to 0 of, all right, f of w plus h, that's the square root 3w plus 3h plus 1, minus f of w is the square root of 3w plus 1 all over h. So numerator, notice as h goes to 0, the entire numerator goes to 0 and the denominator goes to 0 as well. Indeterminate form, so time to play the algebraic game. And in this case, we will multiply by the conjugate of the numerator. So I'm going to multiply by 3w plus 3h plus 1 all inside the root, and then switch the signs, plus square root 3w plus 1 all divided by that same thing, so square root 3w plus 3h plus 1, and then plus square root 3w plus 1. So then when we perform that product, that multiplication, we get limit h goes to 0, again on the top. Product of conjugates leaves us with the difference of squares of the terms, which is a 3w plus 3h plus a 1, and then minus the quantity 3w plus 1, all over h times the square root of 3w plus 3h plus 1 plus square root 3w plus 1. And so we can see some terms will go away. 3w minus 3w is goodbye. 1 minus 1 is goodbye. And we are left with a limit as h goes to 0 of a 3h in the numerator over an h times square root 3w plus 3h plus 1 plus square root 3w plus 1. And then h's simplify, they disappear, and the result is a function, 3 divided by that sum of the roots, in which it's not indeterminate anymore. So if we let h go to 0, what do we get? We're going to get a 3 in the numerator and a square root of 3w plus a 1 in the denominator, right? Because, of course, as h goes to 0, the 3h goes to 0 down there. And then plus another square root, 3w plus 1. So then we just add the like terms up in the denominator and get 3 divided by 2 times the square root of 3w plus 1. And so you can see that the whole process is really the same of using the limit definition of the derivative. It's just that what we're asked to find at the very beginning here, ddw of the square root of 3w plus 1, that's that new notation. So we want to be able to identify that, that's just really the same thing as, say, finding f prime of w here. And when we find that result using the process which we just did, the limit definition, of course, this is the same as ddw of the square root of 3w plus 1. So we did it. Very similar process as before. It's just that we got the new notation now. Let's do one more before we end the video. Something that maybe will challenge our understanding of the Leibniz notation. Now, in part B here, there's several things going on. First of all, we got to find the derivative with respect to r here, right? So that dr in the denominator is telling us treat the variable r as the independent variable here, the input variable, right? So we're going to differentiate with respect to that variable r. And what are we going to differentiate? We're going to differentiate the function pi x r squared. So this function right there, let's think of that as an f of r, right? Because we're treating r as the input variable. That's pi x r squared. And then once we differentiate that function with respect to r, we are also going to then evaluate it at r is equal to 2. So if f of r is pi x r squared, really this is just the same thing as finding f prime of 2 here. All right, that evaluation symbol with the bar and r equal to 2 on the right side of this expression is telling us to evaluate the result at r is equal to 2. Keeping in mind that even though we see the variable x here, we are going to treat the x as a constant, just as we will with the constant pi, because the dr in the denominator in this notation is telling us that r is the input variable. Anything else you see is a constant. All right, so that's important. That's important to the notation here, and that's part of why we use this notation. So we still got to find it. Now, remember, think of f prime of 2 as a f prime of a. And so, remember, f prime of a is just the same thing as limit h goes to 0 of f of a plus h minus f of a all over h, where a is now a numerical value versus what we've been using before, where, say, x is a variable. So this is a value of a derivative, not the derivative function. So there's a variety of ways you could do this, right? We could actually find the derivative function f prime of r here, and then once we get that, evaluate it at r is equal to 2. Or we can just do everything at once and find f prime of 2 using the notation right above here. And that's exactly what I'm going to do. So off on the side, I'm going to go ahead and find what f of a plus h here is, noting that a is equal to 2, right? In our case, a is 2. So what is f of 2 plus h in this case? Remember, the r is getting replaced by the 2 plus h. So in my formula, I have f of r is pi xr squared. I'm going to replace r with 2 plus h and get pi times x, replace the r with 2 plus h quantity squared. And since we're going to be subtracting f of 2 from this in our limit, might as well expand that. What do we get? Pi x times a 4 plus a 4h plus an h squared, just squaring the binomial. So let's go ahead and set up the whole limit here. F prime of 2, what is it? It's the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. Right? Now we just found f of 2 plus h, so let's replace that. Limit h goes to 0. F of 2 plus h is pi x times the quantity, 4 plus a 4h plus a h squared. And then we got to subtract f of 2 from that. So we didn't find that yet, but just off on the side as well, notice that f of 2 is just the same thing as pi times x times 2 squared, replacing r with 2, which is 4 pi x. Right? So that's my f of 2, and I will subtract that from the quantity I've already written down in the numerator. So subtract a 4 pi x all over h. And then we want to look for terms that are going to cancel. So imagine if I distributed the pi x to everything, then the 4 times pi x, that's going to go away with this, because 4 pi x minus 4 pi x is 0. Nothing else will cancel at the moment, but I'm left with the limit as h goes to 0 of, let's go ahead and distribute the pi x to the remaining terms. So 4h times pi x, and pi x also times the h squared, leaving us with a 4 pi x times an h plus a pi x times the h squared all over h. Now notice here, there's a common factor of an h in the numerator. Go ahead and factor that out and get the limit as h goes to 0 of h times a 4 pi x plus a pi x times an h all over h. And now we can see those h's are going to cancel. And notice that what we're left with here is a 4 pi x plus a pi x h. As h goes to 0, then the pi x h goes to 0, and we are left with 4 pi times x. And that is the same thing as f prime of 2 here, which is equivalent to the derivative with respect to r of pi x r squared evaluated at r is equal to 2. So there was a lot going on there because there's that extra x. We had the constant multiple of the pi. And so really starting with the notation at the beginning, dissecting it and really understanding what are we trying to find here allows us to proceed and find what we need to find. So in this case, the result is a 4 pi times an x. So there's your first lesson on Leibniz notation, and we'll see it a lot more often as we go through the discussions. And of course, we're going to have to look at higher order derivatives with Leibniz notation as well. And then hopefully those last couple of examples there helped give you an idea of just using the notation and finding what we need to find. But that is it for this video. Next video, we're going to start looking at various ways that derivatives can be undefined, what happens graphically in those situations. Until then, this is Math and Beats, and I'm out. Like.